Linear models may be too simple. Why do we say it is too simple? We can imagine that x1 and y may have a more complicated relationship. But for a linear model, the relationship between x1 and y is a straight line. As x1 gets higher and higher, y should get larger and larger. You can set different w to change the slope of this line. You can set different b to change the point of intersection of this blue line and the y-axis. But no matter how you change w and b, it's always a straight line. When x1 is getting bigger, y is always getting bigger too. The more people watched the video on the day before, the larger the number of views on the next day will be. But maybe the reality is not like this. Maybe when x1 is less than a certain value, the number of views on the day before is directly proportional to the number of views on the next day. But when x1 is greater than the value, y goes in the opposite direction. After a threshold, assuming that x1 is too large, the number of views on the day before was too high, then the number of views will decrease on the next day. This can happen too. Maybe between x1 and y, there is a more complicated relationship. A relationship like this red line. But no matter how you adjust your w and b, you can never produce the red line. You can never use a linear model to fit this red line. So what could we do? It is obvious that the linear model has a lot of limitations. The limitations that come from the model are called model bias. Notice that at the beginning of the class, B is also called bias. Here the usages of the two words are a little bit ambiguous. We should emphasize that the limitations are called model bias. It is different from the bias B. It means that, due to the limitations, the model cannot simulate the real situation. So what could we do? We need to write a more complicated and more flexible function with unknown parameters. A linear model is obviously not enough. Then what should we do? How to write a more complicated function with unknown parameters? We can take a look at the red curve. The red curve can be seen as a constant function plus a bunch of blue functions like this. The blue function has a special property. When the input value, the value of the x, is less than a certain threshold, the output is a constant. When it is larger than another threshold, the output is another constant. There is a slope in the middle, so it first goes horizontally, then goes upward or downward, and finally goes horizontally again. Actually, it has a name. We would talk about its name later. Here because it is a blue function. Let's call it the blue function. Okay, so this red function can be seen as a constant function plus a lot of blue functions. Then this constant term, how big should its value have to be? Look at this red line. Where is the intersection with the x-axis? Okay, what about this constant function? Let's set it to be as big as the value of the intersection with the x-axis. Then how to produce the red function? After adding the blue function? You could just add this blue function, its slope. The starting point of this slope is set at the beginning of the red function. Then the end of the slope is set at the first corner. So there is a corner on the red function. Then you have a blue function. The end of its slope is set at the first corner of the red function. And then, you purposely let the slope of this blue function here be the same as the slope of this red function. Their slopes are the same. At this time, if you add 0 to 1, you can get this segment of the red function. The first one to this. The value before the first turning point. So after adding 1 to 0, you can get the part before the first turning point of the red function. Then next, plus the second blue function. How to add it? You could just look at the red line. Where is the second turning point? Okay, so for the second blue function, its slope is between the red function's first turning point and the second turning point. Between the first turning point and the second turning point, then you purposely set the slope of this segment the same as the slope of this segment. At this time after adding 1 and 2 to 0, You can get the line segment between the two turning points. You can get the part of the red function. Next, we look at the third section. How do you create the section after the second turning point? You can add a third blue function. This third blue function will have its slope starting point at the same place as this turning point. The slope here will be the same as the slope here. Okay, then after you sum 0, 1, 2, and 3 up, you'll get the red line. You'll get the red line. So the red line can be seen as a constant, plus a bunch of blue functions. If you think about it, you will find out that no matter what kind of piecewise linear curve I draw. What's a piecewise linear curve? When a given curve is composed of many line segments. When it's composed of many jagged line segments, it is called a piecewise linear curve. You will find that these piecewise linear curves are composed of a constant term and a lot of blue functions. The difference is that they may not use the same blue functions. You need to have many different blue functions. Combine them with a constant. You can create these piecewise linear curves. So if your piecewise linear curves are more complicated, that is, they have more turning points, you will need more blue functions. So, when it comes to this, someone might say, what if the relationship between x and y is not a piecewise linear curve? Maybe it's a curve that looks like this. Even if it's a curve like this, it doesn't matter. We can choose some points on the curve and connect them, transforming them into a piecewise linear curve. This piecewise linear curve can be very similar to the original curve if you choose enough points, or if the locations of the points you choose are favorable. If you choose enough points, this piecewise linear curve can approximate this curve. This continuous curve, it can approximate this curve which is not piecewise linear, but rather a curve with an arc. So we know one thing today. You can use piecewise linear curves to approximate any continuous curve. And every piecewise linear curve can be composed of a lot of blue functions. In other words, as long as I have enough blue functions, I may be able to create any continuous curve. So today, suppose the relationship between x and y is very complicated. That's okay. We can try to write a function with unknown variables. This function with unknowns represents the sum of a bunch of blue functions and a constant. The next question we have to ask is, how should the formula of this blue function look like? How to write the formula of this blue function? Maybe it's not so easy for you to write it out directly, but you can use a curve to approximate it. Which curve should be used to approximate it? We can use a sigmoid function to approximate this blue function. The formula of the sigmoid function looks like this. Its horizontal input is x1. The output is y. We first multiply the input x1 by w. Then we add b. We make the result a negative value and make it e's exponent. We plus 1 to the result and place it where the denominator should be. Divide 1 by 1 plus e to the power of negative b plus w times x1. You can multiply the fraction with a constant called c. Okay, if the value of x1 you input approaches infinity, what will happen? If this term approaches infinity, then the exponential term will disappear. When x1 is very large, the line will converge at the height of c. If x1 approaches negative infinity, what will happen? If x1 is very small, the denominator will be very large. Therefore, the value of y will approach 0. So you can use a function like this to draw this curve, and use this curve to approximate this blue function. The name of this thing is called sigmoid. What does sigmoid mean? Sigmoid, if you have to define it, can mean S-shaped. So sigmoid function is essentially an S-shaped function, because it looks a bit like an S. We call it sigmoid function. Here, we don't even bother to write the exponential out. We just write it like this. Y equals c times sigmoid. Then put b plus w times x1 in the parentheses. What we actually do to this b plus w times x1 is to make it the exponent of e, and add a negative sign in front of it. Then we add 1 to this exponential term, and place it at the denominator. We multiply it by c. And let it equal to y. Okay, so we can use this sigmoid function to approximate the blue function. In fact, this blue function is commonly known as the hard sigmoid. It's just that since we started with the blue function first, rather than the normal sigmoid function, it would be a bit confusing to mention hard sigmoid before we introduce the normal sigmoid function. Thus, we first introduce the normal sigmoid function. Then we say that this function can approximate the blue function, which is commonly known as the hard sigmoid. Now, we need a variety of different blue functions. Remember, to create different curves, we need a variety of suitable blue functions. And how are these suitable blue functions made? By adjusting the variables b, w, and c. By adjusting b, w, and c, you can create different shapes of sigmoid functions. The various sigmoid functions created can then be used to approximate this blue function. For example, what happens if we alter the variable w? The slope changes. More precisely, it changes how steep the slope is. What happens if we alter the variable b? The sigmoid function shifts horizontally, allowing us to move it left and right. What happens if we alter the variable c? The height changes. So, with different values of w, b, and c, you can create different sigmoid functions. After stacking up different sigmoid functions, you can create and approximate all kinds of different piecewise linear functions. Then, the piecewise linear functions can be used to approximate various continuous functions. So, suppose we want to write out the function of this red line. What might it be? We can see that the red line is the result of stacking these four blue functions. As we mentioned earlier, these blue functions are sigmoid functions of different shapes, and can all be written in the form of c1 times the sigmoid of w times x1 plus b. The only differences between these blue functions are the variables, which are w, b, and c. For the variables of the first blue function, we denote it as w1, b1, and c1. For the second blue function, we denote it as w2, b2, and c2. For the third blue function, we denote it as w3, b3, and c3. Then, we add all four functions together. We get a function that looks like this. We add up 1, 2, and 3. This can be written as summation over I, where I equals 1, 2, and 3. Inside this summation over I is ci times the sigmoid of wi times x1 plus bi. So, every formula here represents a different blue function. We use the summation over I to stack these blue functions together and create a new function. Now, don't forget to add a constant, which is represented as b here. Assume that we have a function, and we write it out in this form. If we treat the parameters in this formula, which are b, w, and c, as arbitrary variables instead of constants, then we can set different b, w, and c for each function, and create different blue functions. By stacking these different blue functions, we can make different red curves. And with these different red curves, we can create different piecewise linear curves, which can be used to approximate all kinds of continuous functions. So, we actually have a way to write out functions with unknown parameters that are very flexible. It can be written out as the summation of a bunch of sigmoid functions, each with different c, b, and w. Okay, so originally, we were working with linear models, which can be written as y equals w times x1 plus b. The linear model has a very big limitation, which is called model bias. So, how can we reduce the bias of the model? We can do so by creating a more flexible function with unknown parameters. It can be written as y equals b plus summation ci times the sigmoid of wi times x1 plus bi. Originally, we have w times x1 plus b. Here, it becomes wi times x1 plus bi. By choosing different bi, different wi, and different ci, we can then apply them to this formula and add them all up with b to get y. By choosing different c, b, and w, we can create All kinds of different functions. Okay, we have actually evolved to not just using one feature. We can use multiple features. Here we use j to represent the number of features. For example, if we consider the first 28 days, j is 1 to 28. If we consider the first 56 days, j is 1 to 56. We can expand this function to the one above that we just talked about. The more flexible function, which is also very simple. We just replace the items in sigmoid. Originally, we have b plus summation over j w j x j here. Now, we put this item in the parentheses, changing to bi plus summation over j w I j x j. Put what was originally placed here in sigmoid. Then in each sigmoid function, there are different bi and different wij. Then after applying sigmoid to them, we multiply them by ci, and add all of them up. Then after adding b to them, y is obtained. We just need to put different values for ci, bi and wij here. It can become a different function. Okay, if you still think it's a bit abstract when it comes to this. If you have a bit of headache when looking at the formula. Let's use a more intuitive way to draw out what this formula actually does. It looks like this when it is drawn out. Well, let's first consider the situation where j is 1, 2, 3. That is, we only consider 3 features. For example, we only consider the case of the previous day, the previous 2 days, and the previous 3 days. So j is equal to 1, 2, 3. Okay, so the input is x1, which represents the number of viewers from the previous day. x2 represents the number of viewers 2 days ago. x3 represents the number of viewers 3 days ago. What is I? Each I represents a blue function. Because for each blue function we use a sigmoid function to approximate it. So each I represents a sigmoid function. Or it represents a blue function. Okay, so here. This 1, 2, 3 means we have 3 sigmoid functions. Let's take a look at the thing inside these parentheses. Every sigmoid has parentheses. What's the thing inside these parentheses? The first case with sigmoid I equal to 1 is to multiply x1 by a weight called w11. x2 multiplied by another weight is called w12. x3 multiplied by weight is called w13. Add it all up. Don't forget to add another b. Then add up b. Then the formula obtained is like this. Here we use wij to represent the weight that the jth feature is multiplied by in the ith sigmoid. The first feature is multiplied by w11. The second feature is multiplied by w12. The third feature is multiplied by w13. For the 3 features 1, 2, 3. The second subscript of this w is 1, 2, 3. The first subscript of w represents that now. We're considering the first sigmoid function. And we have 3 sigmoid functions. Okay, for the second sigmoid function. We won't write down its w. We won't put its w next to this arrow. Otherwise, it will be too crowded. The second sigmoid function. What does it do in the parentheses? What it does in the parentheses is to multiply x1, x1, by w21. Multiply x2, x2, by w22. Multiply x3, x3, by w23. Add them all up and add b2. What about the third sigmoid? The third thing sigmoid does in parentheses is to put 1, 2, 3, 1, 2, 3, x1, x2, x3. Multiply them by w31, w32 and w33, respectively, and add b3. Okay, now for simplicity. We use a more simple notation to represent the numbers in the parentheses. So we treat this bunch of things as R1. We treat this bunch of things as R2. We treat this bunch of things as R3. Then for x1, x2, and x3 and R1, R2, R3. What is the relationship between them? You can use matrix and vector multiplication method to create a more simple and concise writing style. We've already known that R1, R2, R3 are the results of the calculation in parentheses. The result of the calculation in the 3 sigmoid parentheses. For R1, R2, R3 and the 3 input features x1, x2, x3. The relationship between them is like this. Multiply x1, x2, x3 by a different weight. and plus different bias. That is, different b will get different r. Then these three formulas, the series of calculations. Actually we can simplify them. If you are familiar with linear algebra, it can be simplified to the multiplication of matrix and vector. Put x1, x2, x3 together into a vector. Put all w here together into a matrix. Combine b1, b2, b3 into a vector. Combine r1, r2, r3 into a vector. Then for these three formulas, you can simplify it so that there is a vector called x. This x multiplied by a matrix called w. There are 9 values in this w, which is the 9w here. It is the 9 weights here. X is multiplied by w, and then b is added to get the vector of r. What is done here is exactly the same as what is done here. There is no difference between them. It's just a different way of expression. Originally, to write the three numbers, there are a bunch of additions and subtractions. A bunch of other superscripts. And 2 subscripts that seem too annoying. Now we replace them with a more commonly used representation in linear algebra. X is multiplied by the matrix W, and the vector B is added. And then we get a vector called R. Okay, so about the operation here. What is done in these brackets is that we multiply X by W and add B to equal R. Which are R1, R2, and R3 here. Oops, the cursor is a bit erratic. That must be a display problem. It's okay. I took back control again. Here are R1, R2, and R3. They will pass through the sigmoid function separately. Okay, pass through the sigmoid function separately. Because what we actually do is make R1 negative. Take its exponential, add 1. And put it in the denominator. 1 over 1 plus exponential negative R1 is equal to A1. We get A2 from R2 in the same way. Put R3 through sigmoid function to get A3. Basically, what we do in this blue dotted frame is get A1, A2 and A3 from x1, x2 and x3. Okay. Next. More concisely. We pass R through a function called sigmoid, which is used. We use this symbol here to represent the sigmoid function. So, we got the vector A. By just passing R1, R2 and R3 through sigmoid function. We directly use this symbol to represent such an operation. Then we have A1, A2 and A3. What's next? The output of the sigmoid function has to be multiplied by Ci and added by B. What we are doing here is multiply A1 by C1, A2 by C2 and A3 by C3. Sum them up and add B. And we have Y finally. Okay, for their vector representation. A1, A2, and A3 form vector A. And C1, C2 and C3 form vector C. Then we can transpose C. Multiply A by C transpose and add B. And we get Y. About this series of operations. The more flexible formula we just wrote does the following, taking input x, the feature vector, multiplying it by the matrix W and adding the vector B to get the vector R. Pass R through sigmoid function to get A. Then multiplying A with C transpose and adding B to get Y. So the operation here, if expressed in terms of multiplications between vectors and matrices, defined in linear algebra, will look like this. The R here is the same as this one. Same for A here. Thus we can put this bunch of things inside this bracket. Similarly, A is put here. After combining these equations, it will look like this. The things above. For a more concise and more flexible formulation, in terms of linear algebra, should be written as the following. X is multiplied by W, added by B, passed through sigmoid. Then multiplied by C transpose and finally added again by B to get Y. The one at the bottom is exactly the one at the top. Only it is more flexible. They are all the same. In different formulations. The one above is a graphical representation. Below is its representation in linear algebra. Actually they are telling the same story. Okay. Next. Before we continue with how to find these unknown parameters, let us redefine our symbols. The X here is the input feature. Here are W, B, C and another B. Although there are two B's, they are not the same. This one here is a vector. while the other is a scalar. Behold that their background colors are different. This one is in green while that one is in gray. Which means they are different. We then take the yellow W, B, C, and the other B, and gather them here. Their values haven't been defined. Thus they are our unknown parameters. Then we flatten all these tensors, and concatenate them to form a long vector. We take out every row of W, or every column of it, be it rows or columns. That doesn't matter. We just take out every column or row of W, and concatenate them to form a long vector, along with B, C and the other B. This long vector is represented by the symbol theta. Theta is quite a long vector. The first value in it is called theta1. The second one is called theta2 and the third is called theta3. Inside theta, some values come from this matrix. Some values are from B. Some values are from C. And some values are from the other B. There's no need for such a division. Anyway, theta refers to all unknown parameters collectively. We will hereafter refer to them as theta. Okay, here we just took the first step. We rewrite the first step of machine learning by redefining a function with unknown parameters. Then we will proceed to the second and third steps. Before we proceed, let's see if you have any questions to ask. Okay, let's see if there is any problem online. I try to answer that. I guess his question is about optimization. When doing optimization, we need to find the parameters to minimize loss. One of the most exhaustive methods is to brute force search of all possible unknown parameters. As we just discussed that there are only two parameters, W and B. So we can brute force search all possible values of W and B. So, in the case of few parameters, you don't even need to use the gradient descent method. No optimization skills are required. But, there will be many parameters in the future. In this example, there are a lot of parameters. W, B, C, and B, and then concatenate them together to get a very long vector called theta. So, you can't use the brute force search method at this time. You need a method, such as gradient descent, to find the parameter that can minimize the loss. I hope this answers his question. Okay, are there any classmates who have questions? Please say. Okay. This classmate's question is that there are 3 sigmoid functions in the example. But why is it 3? Could it be 4, 5, or 6? Yes, the number of sigmoid functions is up to you. The more sigmoid functions, the more complicated piecewise linear function are. Assume that you only have 3 sigmoid functions, which means you can only generate 3 line segments. But, if you have more sigmoid functions, you can generate piecewise linear function. With more line segments, you can approximate the more complex functions. As for how to decide the number of sigmoid functions, this is another hyperparameter that you have to decide it by yourself. We used 3 sigmoid functions in the early example. And that is just an example. Maybe I shouldn't use 3. Because it will make you mistakenly think that the number of input features is 3. So the number of sigmoid functions is also 3. No. You can decide the number of sigmoid functions. Okay. Do you have any questions? Hey, please say. With what sigmoid? Hard sigmoid. First of all, its function may be more complicated for you. You can't write down its function at once. But if you can write down its function, you can actually use the hard sigmoid. You can use it if you want. So, it's not necessary to use the sigmoid that we just discussed to approximate the hard sigmoid. There are many other ways. We will talk about other methods later. Okay. Do you have any questions? Okay, if there is no question at the moment, we will continue. You know that this class ends at 6:20. So I can talk about it before 6:20. If you want to leave early, No problem, our courses are all recorded. Okay, then we will move on to the second step. We have to set loss. After having this new model, will our loss be different? There is no difference, the method of definition is the same. We just changed our symbol a little bit. Before, it was L of W and B. Because W and B are unknown. Now, we have a lot of unknown parameters. It is too tiring to list them one by one. So, we directly use theta to set all the parameters. Use theta to represent all unknown parameters. So, our current loss function becomes L of theta. This loss function is to answer how bad or good it will be if this theta is a certain set of values. The calculation method is exactly the same as the case that there are only two parameters, given a certain set of WBCT and B, which means given a certain set of theta values. Suppose that you know the value of W. Substitute W with its value. Substitute B with its value. Substitute C with its value. Substitute B with its value. Substitute X with a feature value. And then see the Y you estimated. And then calculate the gap with the real label. You get an E. Add up all the errors. You get the value of the loss. The next step is optimization. Is there any difference between this optimization problem and the previous one? There is no difference. They are still the same. So, even if we change to a new model, this optimization step, the optimization's algorithm is still gradient descent. It seems that there is not really much difference. Our current theta is a very long vector. We express it as theta 1, theta 2, theta 3 and so on. We are now looking for a set of theta. This theta can make our loss as small as possible. The set of theta that can make the loss the smallest is called theta star. Okay, how do you find the theta star? We have to randomly choose an initial value at the beginning. Here we called it theta 0. You can choose it randomly. Later in this lesson, I might also talk about it. I will also talk about a better way to find the initial value. Let's choose it randomly now. Okay, then you have to calculate the differential. You have to deal with every unknown parameter. Here is represented by theta 1, theta 2, theta 3. You have to calculate its differential to L for each unknown parameter. After calculating the derivative of L with respect to every parameter, it makes up a vector altogether. We use G to represent this vector. Suppose there are 1000 parameters. Then the length of this vector is 1000. There are 1000 numbers in this vector. This vector has a name. This vector, which is made up by putting it all together with the differential of each parameter to L, has a special name. We call it gradient. Well, in many cases, you may see that a gradient is expressed like this. You put an inverted triangle in front of L. It represents gradient. And this is an abbreviation of the gradient. In fact, what I want to express here is this vector. Putting an inverted triangle in front of L means taking all the parameters, including theta 1, theta 2, theta 3, and differentiate L with respect to each of them. That's the meaning of this L inverted triangle. As for the theta 0 behind, it means that the position we take differential is where theta is equal to theta 0. Where theta is equal to theta 0. After we calculate this gradient, calculating this G, we update our parameters. In the next step, the update method is exactly the same as in the situation with only two parameters previously. We just need to change the number of parameters from 2 to, say, 1000. But the update method is exactly the same. If there is originally a parameter called theta 1, the superscript 0 means it is a starting value, which is a randomly selected starting one. Theta 1 0 minus learning rate, multiplied by the value of the derivative. Then you get theta 1 1, which represents the result of theta 1 updated once. Theta 2 0, subtracted the derivative and multiplied by. Subtracted by learning rate and multiplied by the value of the derivative. Is theta 2 1. And so on. Now you can update all the 1000 parameters. Here comes an abbreviated notation. That is, you can combine all the thetas here as a vector. And we use theta 0 to represent it. As for here, you can take out the learning rate. The remaining part, the differential part, The differential to L with respect to each parameter is called gradient, called g. So, theta 0 minus the learning rate times g is theta 1. We collect all the thetas here. Collect all the thetas here. And call it theta 1. Theta 0 minus the vector theta 0 minus the learning rate, multiplied by g, which is also a vector, is theta 1. Suppose you have 1000 parameters here. Then theta 0 has 1000 values. It's a 1000 dimension vector. G is a 1000 dimension vector. Theta 1 is also a 1000 dimension vector. Okay, this is the whole algorithm. That is, you calculate the gradient from theta 0. Updating theta 0 to theta 1 according to the gradient. Then, calculate the gradient again. Updating theta 1 to theta 2 according to the gradient. Calculate the gradient once again and update theta 2 to theta 3. And do it so on, until you don't want to do it anymore. Or until the gradient you calculated is a zero vector, causing you cannot update the parameters anymore. But, in practice that's almost impossible to encounter a result of zero vectors. In most cases, you stop just because you want to stop. Okay, but in practice. Here comes a detailed issue of implementation. The reason why I mention it here is that there is a paragraph about it in TA's code. So, we'd better explain it here, so it will not confuse you when you read TA's program. In fact, when we perform gradient descent, we will do the following. Suppose we have n pieces of data here, capital N. We divide the n pieces into individual batches. We divide them into batches, into groups. How to divide them exactly? Just divide them randomly. Okay, so there are capital B pieces of data in each batch. And there are n pieces of data in total. Now group them into B pieces. Group them into B pieces. Each group is called a batch. How to group them? Just group them however you want. Just divide them as you like. Originally, we calculate a loss by taking the entire data. Now, we don't do that. We only take the data in one batch. Just take the first batch and calculate a loss. And we call it L1 here, in order to distinguish it from the L here, since it might not be the same. If you calculate the loss by considering the whole data, or only a batch of them, here we use L1 to represent the latter. But, you can suppose that if this B is big enough, maybe L and L1 will be very close to each other. Therefore, in a real implementation, each time we choose a batch first, using this batch to calculate L1, calculating the gradient according to this L1, and update the parameters by the gradient. Then, select the next batch to calculate L2, calculating the gradient according to L2, and update the parameters. Select another batch to calculate L3, calculating the gradient according to L3, and use the gradient calculated by L3 to update the parameters. Hence, we do not calculate the gradient by the capital L. In fact, we calculate the gradient using L1, L2, and L3 from batches. Processing all the batches once is called an epoch. Each time we update parameters, we called it an update. When you read papers, you often see the term update and the term epoch. Update is different from epoch. Each time we update parameters, we called it an update. Processing all the batches is called an epoch. In order to. As for the reason to divide data into batches, let's talk about it next week. But in order to let everyone know more clearly the difference between update and epoch, here is an example. Suppose we have 10,000 data. That is, big N is equal to 10,000. Suppose the size of our batch is set to 10. That means the big B is equal to 10. Here is a question for you. In an epoch, how many times do we update the parameters in total? You can count the number of batches formed from these 10,000 examples. A total of 10,000 divided by 10 is formed, which is 1,000 batches. So in an epoch, you have actually updated the parameters 1,000 times. So we do not update the parameters once in an epoch. In this example, we have updated the parameters 1,000 times in an epoch. The second example. Suppose there are 1,000 data. The batch size is set to 100. In fact, the batch size is also determined by you. So we have one more hyperparameter here. The so-called hyperparameter is a parameter decided by yourself. Parameters set by human, not machine, is called hyperparameter. We have learned today that learning rate is a hyperparameter. The numbers of sigmoids are also hyperparameters. The batch size is also a hyperparameter. 1000 examples. The batch size is set to 100. How many times are its parameters updated in an epoch? 10 times. So when someone told you that he or she did an epoch training, you actually don't know how many times the parameters are updated. Maybe 1000 times. Maybe 10 times. It depends on how big its batch size is. Okay, we can actually make more variations on the model. A classmate asked me just now, is this hard sigmoid bad? Why do we have to change it to soft sigmoid? You don't really have to switch to soft sigmoid. There are other ways. For example, the function formula of this hard sigmoid is a bit difficult to write down. Actually, it's not that difficult to write. It can be viewed as the sum of two rectified linear units. The so-called rectified linear unit is like this. It has a horizontal line. There is a turning point somewhere. Afterward, it becomes a slope. The formula of this function is written as c multiplied by max 0, b plus w x1. This max 0, b plus w x1 means that viewing which is greater between 0 and b plus w x1, the larger one will be used as the output. So if b plus w x1 is less than 0, then the output is 0. If b plus w x1 is greater than 0, the output is b plus w x1. In conclusion, this line can be written as c max 0, b plus w x1. By using different w, different b, different c, you can move its position. You can change the slope of this line. Then this kind of function in machine learning is called rectified linear unit. Its abbreviation is called ReLU. The name pronounces interesting. It really pronounces ReLU. If you stack two ReLUs, it becomes hard sigmoid. Isn't it? We stack a ReLU like this on a ReLU like this. Add them up produces hard sigmoid. So can we use ReLU? Yes, we can. So if we want to use ReLU instead of sigmoid, just change the occurrence of sigmoid to max 0 by plus summation over jwijxi. There were only I sigmoid before. But we need two ReLUs to synthesize a hard sigmoid. So there are I sigmoid. If ReLU has to do the same thing, you may need 2 times of ReLU. Because 2 ReLUs combined is a hard sigmoid. So 2 times of ReLU are required. So we changed sigmoid to ReLU. We change a formula here because we want to represent a hard sigmoid. It means that the blue function is not the only method. You can use other methods. Okay, this sigmoid or ReLU, they are called activation functions. In machine learning, they have their names. They are collectively called the activation function. Of course, there are other common ones. There are other activation functions. But sigmoid and ReLU should be the most common activation function today. We'll talk about which one is better next time. Which one is better? I chose to use ReLU for the next experiment. So obviously, ReLU is better. As for why it is better, that's for next week. Okay, then I did this experiment with all the real data. I did this experiment literally. Suppose we have a linear model with 56 days of data. The loss on the training data is 0.32 K. The loss on the unseen data in 2021 is 0.46 K. If you use 10 ReLU functions, it doesn't seem to have much improvement. The result is similar to the linear model. So it seems that 10 ReLUs are not enough. There is a significant difference between 100 ReLUs. Loss of 100 ReLUs on training data can be reduced from 0.32 K to 0.28 K. With 100 ReLUs, we can create more complicated curves. Originally, linear is a straight line. But with 100 ReLUs, we can generate a piecewise linear function with 100 polylines. It also performs better on the testing data. Next, we change to 1000 ReLUs. With 1000 ReLUs, The loss is lower on the training data. However, with unseen data, it doesn't seem to have much improvement. Okay, what else can we do next? We can modify our model again. For example, we mentioned that A is calculated from multiplying x by w plus b, then pass through the sigmoid function. But we already know that sigmoid function is not necessary. You can also get A by passing through the Rey-Lew function. We can do this process several times. We just multiply x by w plus b, then pass through a sigmoid function to get A. Now we can multiply A by another w prime plus another b prime, then pass through the sigmoid function, or Rey-Lew function, to get A prime. So we can get A by doing a series of operations on x. Next, perform a series of operations on A to generate A prime. Then we can do it over and over several times. How many times to repeat is another hyperparameter. You should decide by yourself. Should you do it twice, 3 times, 4 times, or 100 times? It's your call. Notice that w and w prime are not the same parameter. B and b prime are not the same parameter. They are additional parameters. Okay, then I carry out the experiment. We add 100 Rey-Lews every time. Input features are the data from the past 56 days. If it only repeat once, just multiply w and add b. Then pass through Rey-Lew or sigmoid. If you repeat once, the result is exactly what we just saw. Repeating it twice, the loss has dropped a lot. From 0.28K down to 0.18K. The performance on the unseen data also improved slightly. With 3 layers, there is further improvement. Decrease from 0.18K to 0.14K. From a single layer, which is multiply w once. Then pass through Rey-Lew once. Then pass through Rey-Lew 3 times. We can decrease the loss from 0.28K to 0.14K. On training data. On the unseen data, it reduced from 0.43K to 0.38K. This seems to be a little better. Okay, this is the result of the real experiment. Let's take a look at what the result of passing Rey-Lew 3 times is. The horizontal axis that has been discussed is time or day. The vertical axis is the number of people who watched. The red line represents the real data, and the blue line is the predicted data. One can observe the low point in the data. The data in red reach a 2-day low point every once in a while. At the low point, the machine's prediction is fairly accurate. It can accurately predict which 2 days are low. These 2 days are low. These 2 days are low. These 2 days are low. There is an interesting thing. This machine overestimates the number of real viewers, especially on this day. There is a very obvious low point on this day. But the machine did not predict that there will be a significant low point. It predicts the low point 1 day late. Do you know what's going on? No, it's not leap year. Because it's not yet February 28th. Do you have any ideas? Right, New Year. What's the lowest point of the day? The lowest point of the day is New Year's Eve. Who learns machine learning on New Year's Eve, right? So you can't blame the machine for this mistake. It doesn't even know what New Year's Eve is. It only uses the data of the previous 56 days to predict the numbers for the next day. So it doesn't know that it's New Year's Eve that day. Thus you can't blame it for its inaccurate predictions. Okay, so far, we've discussed various models. But we still have one thing missing. Do you know what's missing? We're missing a good name for the models. As all of you know, appearance is very important. A weeb can be good looking after wearing a suit. Any random people could sound freaking dope if he had a long and fancy name. Right? So our model also needs a good name. So what is its name? These sigmoids or Rey-Lews. We call them neuron. We have a lot of neurons here. And we give many neurons another name. Neuron network. What is a neuron? Neuron originally refers to the nerve cells in our body. There are many neurons in the human brain. Many neurons connected together form a neural network, which works similarly to your brain. Then you can lie to all those muggles. My models simulate the human brain. My models simulate the human brain. This is artificial intelligence. Then muggles will be scammed and give you all their money. But this trick had already been used back in the 80s and 90s. Neural network is not a new technology. It has already existed since the 80s. The reputation of it was damaged at that time, because the power of neuron networks was too exaggerated. Everyone is sick of hearing the name neuron network. It's like a dirty word. If written on a research paper, your paper is destined to be rejected. So in order to restore its glory, what should we do? We need to give it a new name. What is the new name? Well, we have a lot of neurons here. So we call each row of neurons a layer, or also hidden layer. And when we have many hidden layers, we call it deep. So this large network is called deep learning. Okay, so now you know what's deep learning. After all, that's it. That's how the name is born. Okay. Then people started to pile up the neural network with more and more layers. In 2012, a network called AlexNet had 8 layers. And its error rate is 16.4%. 2 years later, another network VGG, with 19 layers, achieved 7.3% error rate in image recognition. Those results are judged with a benchmark database in image recognition. Later on, GoogleNets managed to obtain 6.7% error rate, with 22 layers. But these are nothing. Residual Net has 152 layers. Even higher than Taipei 101. But in fact, training such deep networks requires some tips and tricks. We will talk about this later. So far, if you think about what you have learned until now, have you found anything strange? I don't know if you have noticed the strange part one was talking about. We said at the beginning that we want to use ReLUs or sigmoid to approximate a complex function. In fact, as long as we use enough ReLUs and sigmoids, any continuous function can be approximately produced, right? We only need to have enough sigmoids to produce a function with lots of line segments, and thus approximating any continuous function. So we only need one row of ReLU and one row of sigmoid, actually. Then what's the purpose of adding layers? What are the benefits of stacking them repeatedly? Why not just line them up in a row? It can also represent any function, so it makes no sense to use it repeatedly. So some people say that deep learning, which uses ReLUs and sigmoids repeatedly, is just a gimmick. The reason why people like deep learning is just because deep is a nice name. If you line up ReLUs and sigmoids in a row, you only come up with a fat network. Fat neural network. This sounds so much lamer than deep neural network. Deep sounds better. Fat neural network sounds like some weeb neural network. Not good. So why is deep better? Why don't we make the network fatter, but make the network deeper? This is a topic we will talk about in the future. Okay. Then, some other people said, why don't we make it deeper? We only stacked 3 layers. The number of layers should be way more than this. Networks now normally have hundreds of layers. You should be embarrassed if you release a network without hundreds of layers. After all, you're doing deep learning, right? Okay, so let's make it deeper. So, we actually make it deeper. 4 layers. 4 layers for the training data. Its loss is 0.1 K. On the 2021 data that haven't been read. How is it? It's 0.44 K. How could it be that we have such a miserable loss on training data? 3 layer is worse than 4 layer. And 4 layer is better than 3 layer. But on the data that haven't been read, 4 layer is poorer. And 3 layer is better. On the data that haven't been read, on the training data, and the unread data, there are inconsistent results. This kind of training data and unread data, also known as training data and test data, have inconsistent results, is called overfitting. Then you may hear people saying that Overfitting occurs in machine learning training. It refers to the accuracy improving on the training data, while not on the unread data. So far, we haven't exerted the real power of this model yet. You know that we want to exert the power of this model, and the data from 2021 to the latest February 14th. We already have. So, what are we going to do? What we are going to do is to predict the unknown data. But, if we want to predict unknown data, should we choose 3-layer network? Or 4-layer network? For example, today is February 26th. The number of viewers today is unknown. If we want to use a neural network, which we have trained, to predict the number of viewers today, will you choose 3-layer network? Or 4-layer network? Okay, let's ask your opinions. If you choose the 3-layer network, please raise your hands. Good, and hands down. If you choose the 4-layer network, please raise your hands. Good, it's less. As for how to choose a model, that is what we are going to talk about next week. Everyone, I know that most of you have a very sense of this topic. You know that we have to choose a 3-layer one. Most people choose a 3-layer one. You might want to ask why not the 4-layer one. The result on training data from 4-layer network is better. In fact, we don't care about the result of the training data. What we really care about is the result of the unread data. And it is unread data on February 26th. While training, we should choose the model that performs well on unread data. So, we should choose the 3-layer network. Then, you might think that we are going to end the course. Actually not, let's predict it practically. How many views should you have on February 26th? Please note that it's from YouTube statistics. It's not so real-time. Thus, it only computes the data till February 24th. It's okay. Let's first calculate the number on February 25th. What is the number of viewers? This 3-layer network told me that the total number of viewers of this channel on February 25th is 5,250. We assume that it's right on February 25th. Actually, we don't know, because the statistics back end has not yet been released. But, we still assume that it is all right this day. And then we let our model predict the number of viewers on February 26th. The result is 3,960. Why is it so few here? It's because the model knows that the number of people watching this Friday is relatively few. So, it predicts very few. Sounds reasonable. But, what do you think about this prediction? Comparing to 380 here? Which one will be more accurate? What do you feel? What do you think? Let's take a look next week. What is the actual value on February 26th? But, if you think this value, whose error comparing to the true value, is less than 380, please raise your hands. Is greater than 380, please raise your hands. Wow, good. Hands down. It seems that you don't have much confidence in me. Okay, let's take a look at how much error it will be next week. Of course, I don't expect that it will be accurate. By seeing so many people stand for the greater error. If everyone here goes to click that video, wow, the error is great. Why am I saying that so long? The reason is I'm trying to seduce you to click the videos. Well, I actually only talked about deep learning today. It's not a traditional way to talk about it. If you want to listen to the general way of introduction, the lecture videos from the past are also available online. I will attach the link here. By the way, deep learning training used a thing called backpropagation. In fact, it is a method that is more efficient than the method of calculating gradients. There is no difference to what we have taught today. But, if you really want to know what backpropagation is, the video link is also attached here. Okay, that's all about today. Thanks for your listening. Thank you.